In this video, we're going to discuss the interpretations of the derivative. We've already discussed the derivative at a point and the derivative function, right? Where we have the instantaneous rate of change for all values of x, where we can calculate the derivative at any point where your function and your derivative is defined. And so what we want to do is we want to get to interpretations, but with the interpretation, sometimes having an alternate notation will help us better interpret the derivative. And so it says if f of y equals f of x, then we can write the derivative as f prime of x. And we said before that our derivative at a point is the slope of the tangent line, right? And your slope of any line is you're changing your y over your change in x. So your derivative still carries that meaning in the background. What we're going to do with this alternative notation here is that we're going to start presenting this change in y over change in x, or we can also write f prime of x using dy over dx. All right, that's dy over dx, right? So this is your Greek letter delta, that triangle, and so that's a Greek letter for d. And so instead of using the Greek letter delta y, we can use dy over dx. And this is true as for smaller and smaller intervals around x. And so when delta x, your delta x's are very, very small. This notation is attributed to Leibniz. Some people call this Leibniz notation. And it's useful for interpreting or determining the units of your derivative, right? If you write your derivative, instead of using f prime of x as dy over dx, you can see that in the numerator you have a y, and in the denominator you have an x. And so your derivative is always going to be the units of your numerator, which is y, divided by your units of your denominator, which is x. One of the inconvenient things about this derivative, for instance, if we want to find a derivative f prime of 2 evaluated at some point 2, x equals 2, then if we wanted to use this notation, the Leibniz notation, to do that, we would write this as dy over dx, and we will put a vertical bar and to tell everyone else that you're evaluating that at, let's say, x equals 2. All right. And so that's how we would use this notation. This is a lot to write, and so that's why people say that this is inconvenient, but it's definitely convenient for determining your units. It's easier to say, oh, evaluate your derivative at this point using this notation, and then getting your units, we'll use this Leibniz notation here. All right. You can also think of d over dx or d dx as an operator, which instructs you to find a derivative with respect to the variable in the denominator, right? So let's say we have a function y equals f of x. Then when I want to find my derivative, I can say, oh, well, I'm going to do the derivative of this function f of x with respect to x, right? And this is saying this notation here means, oh, do the derivative. So it's almost like it's an operator, almost like adding or subtracting or multiplying or dividing. But we say it's an operator because it's done to a function. So if I wanted you to do a derivative with respect to the variable t of a function, I can say, oh, do d dt of some function. I'm just picking a random function here, g of t. That means go to the algebraic form of that function and do the derivative with respect to this variable that's sitting here. All right, and so that's some other notation that's relevant to the Leibniz notation here. Our goal in this section is to go through a full review of how we can interpret the derivative. And so we're going to, for the rest of this section, we're going to look at several example problems where we do just that. And so in example 1, it says, suppose s of t is the height in meters of a ball t seconds after being thrown into the air. Find the units of s prime of t. Now, you don't always have to necessarily do this. Notice here, our output is s, our input is t. T is in seconds, s is in height. And so if I wanted to, I could write the derivative of this function using Leibniz notation. My input variable is t, right? So you know how we have dy over dx? Well, my input variable always goes in the denominator, and my output variable, which is the s, goes in the numerator, right? So it doesn't say y equals, so I'm going to call my output s, because that's the function's name. And so my S prime of t is the SDT. And this is a convenient way for me to see my units here because it's always the units of your numerator here divided by the units of the variable in the denominator. And so our units in this example, what S is the height, is going to be in meters. So it's going to be meters. And then that's going to be divided by, or we can say per, and then the units of t is in seconds. So it's meters per second. All right, that's the units. Interpretation of the derivative, I'm going to type this out actually. And so when we interpret the derivative, we have to think about what it means for s prime of 2 to be equal to 15, right? And so remember, when we're dealing with the derivative, we're dealing with instantaneous rate of change, right? It's at that instant, okay? And so what I'm going to say at 2 seconds, I'm going to use the number, 2 seconds after being thrown in the air, my output represents the height of the ball. The height of the ball is, since that derivative is positive, I'm going to say increasing. And I'm going to put the actual number, 15, and my units are meters per second. Okay? So at 2 seconds after being thrown in the air, the height of the ball is increasing at 15 meters per second. This is the exact same interpretation that we've given in section 2.1. All right. Now what I'm going to do is I'm going to slightly change that interpretation because there's actually one more interpretation that we're going to look at. And it's going to be related to what the derivative means graphically. Remember that when we have a derivative, all right, for instance, I'm going to come over here just to do a little bit of scratch work, okay? When we have a derivative, I don't know what this function looks like. It may look something like that. A ball is going to be thrown in the air. It's going to go up and it's going to come back down, right? Let's say 2 seconds later, it's over here. So let's say that this is t equals 2. And, well, it can't be that because our derivative is positive. And so what I'm going to do here is I'm going to change this ever so slightly. All right. Let's say x equals 2 is here. Then our derivative, right? Remember, it always represents your slope of your tangent line, right? At that point where x equals 2, right? And so I'm going to draw a tangent line. All right, it's pretty steep and it's a pretty bad tangent line here. I do apologize. And so basically what this derivative at x equals 2 is basically telling me is that the slope of this line is 2. Now, if I go back and think about how I interpret the slope of a line, I could interpret this derivative in this way here. Remember the slope of a line, for 1 unit increase in your input, your output would increase by the value of your slope if it's positive, or it'll decrease by the value of your slope if it is negative, right? And so I could say if the number of seconds, that's my input value, increases from 2 to 3 seconds, right? That's a 1 unit increase in your input. Then your output, which is the height of the ball, is expected to, or I'm just going to say will, and since that's positive, increase by 15 meters. And that is an alternative way to interpret your derivative. All right. So there's 2 ways. One way that we've already been discussing, the instantaneous rate of change at that point. So we can say at 2 seconds after being thrown in the air, the height of the ball is increasing at 15 meters per second. Or we can say, okay, well, let's use the interpretation from the slope that says that, oh, if my slope is positive, for a 1 unit increase in my x, my y's will increase by whatever our value of our slope is, right? And so 1 second from 2 seconds to 3 seconds represents that 1 unit increase in our input. Then our output would increase because it's positive by 15 meters. Notice here, I didn't say by 15 meters per second. I said 15 meters. All right. Part C is very similar. It's basically asking me it says the SDT given t equals 5, or the SDT such that t equals 5. equals -7, right? This is that Leibniz notation that we can use to evaluate our derivative at a point. It's almost identical to saying f prime of whatever this value here is, right? So if you don't like that notation, it's basically saying find or interpret s prime of 5 equals -7. All right. Now, this time I'm going to just give the second interpretation. I'm not going to give the first interpretation, but basically it's saying that if the number of seconds, let's type, since the ball, okay, I didn't write this the first time, since the ball was thrown in the air increases from 5 to 6 seconds, right? And I chose 5 to 6 because our t equals 5 here. We're finding s prime of 5, right? Then the height of the ball will decrease by 7 meters, and that's it. I'm not going to say meters per second because that change of one from 5 to 6 seconds takes care of that per second. And so, and also I didn't put a -7 there because I used the word decrease, right? And so that takes care of that. And so that's that interpretation. Let's look at another example. It says, if t, capital T equals f of lowercase t, gives the temperature in degrees Fahrenheit, right? So this is in degrees Fahrenheit, of a frozen pie after being placed in the oven for t minutes. That's minutes. And so our goal is to write a sentence to explain the meaning of f of 2 equals 50. Now we have to start to be careful here. That says f of 2. It doesn't say f prime. So it's just interpreting the regular function, not the derivative. And so since 2 is our input value and our input value is in minutes, so that means 2 minutes after being placed in the oven, our output is degrees Fahrenheit, the temperature in degrees Fahrenheit. So the temperature of the pie is, of the frozen pie, well, it's no longer frozen anymore, it's 50 degrees. And so we can say '50, and I don't have the symbol, so I'm going to write the words degrees Fahrenheit. All right, so 2 minutes after being placed in the oven, the temperature of the pie is 50 degrees Fahrenheit. It says give the units of f prime of t, right? Again, you don't necessarily have to do this, right? But what I'm going to do here is I'm going to use Leibniz notation so that I can get my units of my function, right? So my input value is lowercase t, my output value is capital T. And so I have a d capital T over d lowercase t. That means it's going to be the units of capital T divided by the units of lowercase t. And so my units in this example will be degrees Fahrenheit per minute. Degrees Fahrenheit per minute. And so with that being said, let's go ahead and continue, and let's go to part C, where we will write a sentence to explain the meaning of f prime of 2 equals 8. So again, this is looking at the derivative, right? There are multiple ways in which we can interpret the derivative. The way I'm going to interpret the derivative here is, I'm going to do it both ways, right? We can say at 2 minutes after being placed in the oven, the temperature of the pie is increasing because that's a positive 8. And I'm going to give the actual rate at 8 degrees Fahrenheit per minute. All right. That is an interpretation of the derivative. All right. The other interpretation that I'm going to give is the one that's more useful. All right. When you think about changing that, using that interpretation of the actual slope, it is more user-friendly or more applicable than saying, oh, it's just increasing at 8 degrees Fahrenheit per minute, right? What that means is that if I increase my number of minutes after it's being placed in the oven from 2 minutes to 3 minutes, so I'm going to say if the number of minutes after being placed into the oven increases from 2 minutes to 3 minutes, then the output, the temperature of the pie is expected will increase, because that's a positive, by 8 degrees. That's the usefulness of knowing the instantaneous rate of change. And so sometimes people really, really prefer the second interpretation compared to the first interpretation, which we give here. Be able to use both types of interpretation. Both are correct. Sometimes when you do your homework, you'll look at the homework system and they're interpreting it using the first method. And then sometimes when you're doing your homework, you'll see that they're interpreting it using the second method. So know how to interpret your derivative, your instantaneous rate of change, using both ways. Last but not least, we have the weight W in pounds of a child is a function of its age, which is given by the variable A, and that's going to be in years. So we have the function W equals f of A. Part A, do you expect f prime of A to be positive or negative? And you want to explain why. Well, your input is age and your output is weight in pounds, right? And so if you think about a child after they're born, a year later, and then another year later, and then another year later, you usually, expect children to gain weight, right? And so we're going to say that the derivative is positive because as children age, they tend to increase in weight. And whenever a function increases, that means its derivative is positive. And so that's why we're going to say positive here. It says, interpret the meaning of f of 8 equals 45. Notice here, this is the function. It is not the derivative. For your function, your A is your age. Your input is A, which is your age in years. And your output is the weight, which is in pounds. And so input 8 years old, a child that is 8 years of age should weigh or weighs 45 pounds. All right, give the units of f prime of A. Again, you don't have to convert this to Leibniz notation. I just like to use it since we're getting used to it. But f prime of A is the same thing as saying dW, that's my output value, over dA, right? And so if I want my units, it's going to be the units of my numerator, which is going to be pounds, divided by the units of my denominator variable A, which is in year. And I use the abbreviation for pounds, LBS, so it's pounds per year. All right, part D, interpret the meaning of f prime of 8 equals 4. Interpret the meaning of f prime of 8 equals 4. I don't know why we have that marked there, but there we do. Well, I'm going to interpret it both ways once again, right? Our input variable is 8. Our output variable is 4, but this is for our derivative. Since 4 is positive, we know we have an increasing function. Since this is derivative, I'm going to say at 8 years of age, the output, which is child's weight, is increasing by 4 pounds per year, all right? That is not as useful, right? And so basically what we can say is if a child's age increases from 8 years to 9 years, then their weight, or his or her weight, will increase by 4 pounds, all right? And so this is probably a more useful interpretation of the derivative because, I expect you to gain 4 pounds over that year. That's a lot more clearer. That's a lot clearer compared to saying, at the age of 8, a child's weight is increasing at 4 pounds per year. I mean, it's basically the same thing, but one might be a little more friendly to the general public. I think the second interpretation would be, all right? And so with that, Now we're actually going to use this second interpretation of the derivative to help us make future estimates, right? And so it says, estimate the value of f of 9. Now, I'm going to go back to my problem here. They tell me nothing about they don't give me a function like f of x equals 3x plus 5. They don't give me an equation to plug 9 in to R12 into in order for me to get the actual age of the student or the value of these functions here at 9 and 12. And so what are we going to do? Well, we could use the fact that we do know in part B that a child that's 8 years of age weighs 45 pounds, right? We also know from part D that if I change the child's age from 8 years of age to 9 years of age, then I should expect the child's weight to increase by 4 pounds. And so if I want to find f of 9, and notice it says estimate here because we're going to be given an estimate here. That's going to be approximately equal to the child's age when they're 8 years of age plus the derivative at the child's age, the derivative when the child is 8 years of age, right? And so in part B, we said that the child was 45 pounds at age 8, and the derivative at 8 was 4. That means if I increase the age by 1 from 8 years to 9 years, I expect the weight to increase by 4 pounds. All right. And so that is 49 pounds. All right. Now, this is an estimation. This is called a linear approximation. It's called a linear approximation. The reason for that is because it's using this interpretation from the slope of your tangent line for your derivative at a point. All right. Now, whenever we look at a graph, and I'm going to draw a graph once again, and I come up with a tangent line, right? Let's say my function looks like this. Everything is just bad about this picture. I'm just going to delete it and start over. So if I have a function here, all right, and I know my tangent line to this function looks something like that, all right? Now, what's happening when I use my derivative in order to approximate my functional value, right? So if this is y equals f of x, and this is my tangent line, which we know the derivative at that point is the slope of your tangent line, right? And your tangent line is supposed to touch this function at this point, but not cross it. So it looks a little weird, but there we go. What I'm using when I use this 4 right here is basically, I'm saying my derivative is 4. That means if I go up 4 units and to the right 1 unit, I'm going to be back on my tangent line. I am not going to be on my actual function, right? That's why we're only estimating f of 9, right? So we know f of 8 is 45, right? So that's a point right there. But when I estimate f of 9, I'm getting a point that's actually going to be on my tangent line, and it's not on my function. That is why it is an estimate, all right? And so this is also why we call this a linear approximation, because I'm using my line here, my linear function, my tangent line, in order to come up with an approximation. In the same way that I found f of 9, I can also find f of 7, all right? Because if my derivative is at 8 is 4, that means at 8, if I increase my years from 8 to 9 years, then or you can go back to this definition too, or this interpretation here. It's increasing at 4 pounds per year, right? Well, if it's increasing at 4 pounds per year and I'm using a linear approximation and I want to go backwards from 8 to 7, then instead of adding that 4 to the 45, I wrote 48 there. My computer's doing something weird. It's being slow. So this is the f of 8. And if instead of adding that 4 to get on my tangent line to go to 9, which is what I did in this one here, if I wanted to find f of 7, I subtract 4 and I get over here to where x equals 7. Now, I know this isn't drawn to scale because that would be 0, but you get the picture. So instead of adding a 4, I'm going to add a -4, or I'm going to subtract 4. And that can give me an estimate, and this is going to be an estimate, that in a child of 7 years of age will be 41 pounds. All right. We found f of 9. We can find f of 10 by basically using the fact that it's increasing by 4 pounds a year, right? So I can find f of 10 by using that f of 8. But this time, since 10 is 2 units from 8, I don't just add this 4 once, right? Because that's a 1-year increase in age from 8 years to 9 years. I need to add another 4 to increase from 8 years to 10 years. So some people write this as 2 times f prime of 8, or you just remember that you're adding that 4 twice. And so a child that is 10 years of age is approximately 53 pounds. And then you can find f of 11, and then you can find f of 12. Remember, 12 is 4 units from 8, so I'm just going to save some time and skip over that. I'm going to have f of 8 plus, well, 12 is 4 units from 8, or I'll add 4 times, basically. And then we get an approximation there that child will be approximately 61 pounds. All right, that concludes this video. We'll see you on the next one.